Hi everybody, I hope this video finds you well. In today's video, we're going to be moving on into Chapter 7 of your textbook, starting with Section 7.1. In this section, we're going to be revisiting a concept we introduced earlier, which was the concept of an eigenvalue. In this discussion, though, we're not only going to sort of redefine and sort of discuss the eigenvalue, we're also going to extend it a little bit with a corresponding concept called an eigenvector. So in this video, we'll sort of talk about the definitions of both of these concepts, the eigenvalue and eigenvector, and then we'll do some examples of making sure that we understand how to calculate both eigenvalues and their corresponding eigenvectors. So to start off with here, we're going to let A be an n by n square matrix. So all of our work here, because we're going to be making use of the determinant, is going to be restricted to square matrices. So an eigenvalue lambda of a square matrix A is a scalar such that there exists non-zero solutions V to this equation, AV equals lambda V. Now, if you think about what this equation is basically saying, this is saying that there's some non-zero vector V such that matrix multiplication by the matrix A is equivalent to scalar multiplication by this eigenvalue lambda. Now, you should notice that there is a restriction to the solutions that we're talking about here. We want it to be a non-zero solution. Obviously, if V was equal to 0, this equation is always trivially true. So we're looking at things that have a non-zero solution. So any solution to the above equation for a given eigenvalue lambda is then called an eigenvector for that eigenvalue. So to basically make sure that you guys understand, because there's a lot of sort of moving pieces here, A is our matrix, V, if it's non-zero, is the eigenvector, and lambda is the eigenvalue. All right, so let's talk about how you would determine eigenvalues and eigenvectors. Now, if you remember back from like Chapter 3 when we first introduced you guys to the concept of an eigenvalue, we know that it's going to be somehow related to the determinant. But now that we have a little bit more formal of a definition, let's see how that alternate definition that we saw back in Chapter 3 actually comes about. So, from the above, right, an eigenvalue is a scalar so that the following equation has at least one non-zero solution. So we're starting with this equation, AV equal lambda V. Obviously, if we bring that lambda V onto the other side, we get this vector equation. AV minus lambda V must be equal to 0. And of course, the 0 on the right-hand side there is not the number 0, it's the 0 vector. All right, but let's be a little bit sort of clever with this. Let's actually treat this lambda V as a matrix multiplication. So what we're doing in this step is we're actually viewing lambda V as equal to lambda times IN times V. You can always use that sort of identity matrix because that's not going to change anything. But the reason that we're sort of doing it like this is that this is a vector, but this views that vector as a matrix multiplication. Once you do that, then you can factor that V out and get this expression. A minus lambda IN times V must be equal to the 0 vector. So the trick there is we're just viewing that lambda V as lambda times the identity matrix times the vector V. And then once we have that, we can sort of right factor out that vector V. Now, if we think about this equation here, this is a homogeneous system of equations, right? It's a matrix times a vector equaling the 0 vector. Furthermore, A minus lambda IN is, of course, a square matrix. So remember, when you have a homogeneous set of equations, you know it will always have solutions. The question here is it going to have non-zero solutions? Well, if there's a unique solution to a homogeneous system, then that unique solution is just the 0 solution. But if there's infinite solutions, then some of those infinite solutions will be non-zero. So the only way that we're going to have infinite solutions to this homogeneous system is if we have something that doesn't have full rank. In other words, if this A minus lambda IN is not invertible. So that we can phrase that in terms of the determinant. Something is non-invertible if the determinant is equal to 0. So in other words, we're saying this guy will only have non-zero solutions if the determinant of A minus lambda IN is equal to 0. And actually, this definition right here was the one we stated way back in Chapter 3 for the definition of an eigenvalue. We said an eigenvalue was anything that made the determinant of A minus lambda IN equal to 0. So now we've seen how that definition you guys were exposed to in Chapter 3 is the same as the definition that we're giving here. So this gives us an alternate definition of an eigenvalue. So an alternate definition of an eigenvalue, besides being one that has those non-zero solutions, is anything that makes the determinant of a minus lambda in equal to 0. The eigenvectors, then, for that given eigenvalue are then the solutions to that homogeneous system of linear equations back up here. So those v, any of those non-zero v, would be the eigenvectors. So this gives us two ways to sort of think about it. This is often the definition we will use when sort of working with eigenvectors and eigenvalues, once we sort of have them, if we're trying to prove something based on them. But if we need to calculate them, we usually start with using this, the determinant of a minus lambda in equals 0. That'll allow us to find the eigenvalues. And then we solve this to actually find the eigenvectors. And we'll see that in just a few moments when we start doing our examples. But before we do that, we want to do just a couple little more propositions and another definition. So, proposition, just as a quick sort of thing about eigenvalues and things like that. A n by n matrix A is invertible if and only if 0 is not an eigenvalue of A. So we know a lot about a matrix being invertible. We know that that corresponds to the determinant being non-zero, so on and so forth. Now we're getting another way to sort of think about invertibility. Invertibility is the same as not having 0 as an eigenvalue. So let's go ahead and prove this. It is a if and only if, so we have two directions here. It's a sort of unique little proof. Your book sort of skips proving this because it's a pretty simple proof, but it's sort of interesting because actually the best sort of logical way to prove this is to use a pair of proof by contradictions. So let's go ahead and see that. So our first direction here, which is going to be the sort of forwards direction, is we have A is invertible, and we need to show 0 is not an eigenvalue. So we're going to show this sort of direction first. We're going to assume that A is invertible, and we're going to show that 0 is not an eigenvalue of A. So we're actually going to do this as a proof by contradiction. So proof by contradiction. So we're going to assume the opposite of our need to show. We're going to assume 0 is an eigenvalue of A. Well, if 0 is an eigenvalue of A, then what that means is this means that the determinant of A minus 0 times in is equal to 0, right? The definition of an eigenvalue that we just showed on this is you can think about it like this, or you can think about specifically just for eigenvalues that the determinant of A minus lambda in must be 0. So this means the determinant of A minus 0, since we're assuming 0 is an eigenvalue, must be equal to 0. But if we then think about that, that means that the determinant of A equals 0, because 0 times the identity matrix is just going to be the 0 matrix, so subtracting it from A isn't going to change anything. And that means that the determinant of A must be equal to 0. But that's a contradiction. And that's a contradiction since determinant of A equal to 0 implies A is not invertible. Well, we assumed from the very start that A was invertible, and we got that A is not invertible, so that's our contradiction. So 0 must not be an eigenvalue of A. All right, now let's go ahead and do the opposite direction. So for the opposite direction, we are going to assume 0 is not an eigenvalue of A, and we need to show that A is invertible. Okay, we're going to do the same idea. We're going to do a proof by contradiction. Proof by contradiction. We're going to assume A is not invertible. Okay. Well, if A is not invertible, that means determinant of A is equal to 0. Okay. But if determinant of A is equal to 0, we can sort of bring this over here, and we can view that as the determinant of A minus 0 in equals 0. But if that's the case, right, I mean, again, this is just you recognizing that determinant of A, A is the same as this matrix A minus 0 in. So this tells us that the determinant of A minus 0 in equals 0. But then that tells us 0 is an eigenvalue of A. Well, at the beginning, though, we assume 0 is not an eigenvalue, so this is a contradiction. So A must be invertible. So what this basically shows us is that when we say something, a matrix is invertible, we mean that the determinant is non-zero, and we also mean 0 is not an eigenvalue. Or if you prefer, you can say A is not invertible, which means that the determinant must be 0, which means that 0 must be an eigenvalue. So now you have a way of thinking about it in terms of invertibility, in terms of the determinant, and in terms of eigenvalues. All right, one more definition, and then we'll get into our examples. So let's let A again be a square matrix. Then what we're going to be defining here is what's called the characteristic polynomial of A, which is usually written as P of lambda, is given by that expression, determinant of A minus lambda in. So that determinant there is called the characteristic polynomial of the matrix. Clearly, and as we'll see this in examples, this polynomial is degree n. So if you have an n by n matrix, this polynomial is going to be a degree n polynomial. And the roots of the characteristic polynomial, remember the roots of a polynomial are the things that make this 0. Well, if you make this 0, you're making the determinant of A minus lambda in equal to 0. So those are exactly the eigenvalues. So we can basically sort of rephrase this again, right? Another sort of way of understanding eigenvalues is that they are the roots of this characteristic polynomial. Now, I don't particularly need or make much use of this definition myself, but sometimes your book will reference when you set this polynomial equal to 0, then we call it the characteristic equation rather than the characteristic polynomial. But just know that basically when we want to determine eigenvalues, we'll be setting the determinant of A minus lambda in equal to 0. That's going to boil down to a polynomial equation, which we then should be able to solve. So let's get in and talk about some examples of this. All right. So for the next couple of examples and for the remainder of this video, we're just going to make sure we're comfortable finding eigenvalues and eigenvectors. And again, this is important because eigenvalues and eigenvectors are an important concept in linear algebra in general, and they're an important sort of characteristic or property of a matrix. But it's going to be very important in just about a week or so to find eigenvalues and eigenvectors because we're going to be using that to solve higher order differential equations as well as systems of differential equations. So yes, this is sort of important in of itself, but it's also an important sort of computational skill for where we're headed. All right, so let's find the eigenvalues and eigenvectors of this guy here. So what we need to do is to actually find the eigenvalues. We're going to start with that. So start with eigenvalues. So we need to take the determinant of A minus lambda in and set it equal to 0. So what that means is we're going to be taking the determinant and subtracting lambda in means we're going to be taking lambda off those diagonals. So we're going to be taking the determinant of 2 minus lambda, 1, 1, 1, 2 minus lambda, 1, and 3, 3, 2 minus lambda, and setting that equal to 0. Now, at this point, it's your guys' choice whether or not you want to try to use row operations or just immediately go to like a cofactor expansion. I would be careful with row operations because if you start to do row operations, you're going to be having to do them with these sort of lambdas in there, and it can make things pretty messy. I'll just jump right in and go straight to the cofactor expansion. So I'm going to cofactor expand along the top here. So we're going to have 2 minus lambda times the determinant of 2 minus lambda 1, 3, 2 minus lambda, because once we cofactor there, this will be the sort of minor that we need to look at. Minus, because this guy is going to be in the 1, 2 position, so we'll have minus 1 to the third power there. So we'll have minus 1 times the determinant, and now we'll be crossing those out. So it looks like we will have 1, 1, 3, 2 minus lambda. And then finally plus 1, because this guy is in the 1, 3 position, so his coefficient is going to be a positive 1, times the determinant. And now we'll cross this stuff out. So we've got 1, 2 minus lambda, 3, 3. And all that needs to equal 0. All right, let's go ahead and continue then. 2 minus lambda. Here we can just do diagonal minus anti-diagonal. So that's going to be 2 minus lambda times 2 minus lambda minus 3. Then minus 1 times 1 times 2 minus lambda minus 1 times 3 plus 1 times 1 times 3 minus 2 minus lambda times 3 equals 0. Okay, so there we go. Sorry, it's a little squish there. Oh, there we go, equals 0. Okay, now let's go ahead and start to expand this stuff out and start working on this. A little bit messy, but shouldn't be too bad. 2 minus lambda, we can just FOIL that together. That looks like we're going to get lambda squared minus 4 lambda plus 4 minus 3. And then minus 1. In here, we're going to get 2 minus lambda minus 3 plus 1. And then 3 minus, and we'll have to be careful here because we got to distribute that negative. So we'll just do 3 plus. Looks like we should get 3 lambda minus 6 equals 0. Okay, we can go ahead and then clean things up a little bit. So 2 minus lambda, lambda squared minus 4 lambda plus 1. Distribute that negative, or we'll hold the negative off for just a second. Minus 1 minus lambda, and then plus 1. And looks like 3 lambda minus 3 equals 0. Okay, now we'll go ahead and multiply these things out now. So it looks like we should get 2 lambda squared minus 8 lambda plus 2 minus lambda cubed plus 4 lambda squared minus lambda plus 1 plus lambda plus 3 lambda minus 3 equals 0. And looks like we should get minus 3 lambda for lambda squared. So it looks like we've got 2 lambda squared and 4 lambda squared. So we should get 6 lambda squared. Then we've got minus 8 lambda, minus lambda, so that's minus 9 lambda, minus 8 lambda, minus 5 lambda. So minus 5 lambda. And then finally for constants, we've got 2, and then 3, and then minus 3, so that's going to be 0. So we get equals to 0 there. Okay. Now we've got a cubic polynomial that we'd have to know how to solve here. So in terms of solving that, when we're doing that, right, keep in mind in this case it should be nice and easy because we can just factor a lambda out. But in general, if it's a cubic, you want to try to use the rational roots theorem to sort of find a single root, and then hopefully you can reduce it to a quadratic and then use a more standard approach. But in this case, we can factor out a minus lambda and get lambda squared minus 6 lambda plus 5 is equal to 0. And then it looks like we should get minus lambda, lambda minus 1, lambda minus 5 equals 0. And we can see that we get 3 eigenvalues, lambda equals 0, lambda equals 1, and lambda equals 5. So we've got our 3 eigenvalues there. All right, so now we want to find the corresponding eigenvectors for each of these. So let's go ahead and move on to a new page to sort of take a look at how to do that. So let's go ahead and we'll find eigenvector for, let's start with lambda equals 0, the first one that we got there. So what we need to do is we need to actually consider the equation a minus 0 in v equals 0. So if you think about that, that's going to be removing 0 from the diagonal, so not changing anything, and then solving that homogeneous equation. So let's go ahead and do that. We can jump right into what that's going to look like. That's going to be 2, 1, 1, 1, 2, 1, 3, 3, 2, augmented with 0, 0, 0. Now, here's something that we sort of know about this. As we begin to solve this, we know that it's not going to have a unique solution. In other words, there must be at least 1 0 row in this because we know we have to get some infinite solutions. Otherwise, we would just have the unique solution, which would be the 0 vector, which, because this is supposed to be an eigenvalue and eigenvector, it cannot just be the 0 vector. So let's go ahead and actually find that. So to go ahead and do this, I guess we could make it a little easier on ourselves. We could just interchange R1 and R2 to start with. So we can do 1, 2, 1, 0, 2, 1, 1, 0, and 3, 3, 2, 0. Then we can go ahead and do R2 and replace it with R2 minus 2R1, and R3 and replace it with R3 minus 3R1. And then we get 1, 2, 1, 0. Then we get 0, minus 3, and minus 1, 0. And then down here we should get 0, and then 3 minus 6, so minus 3, and minus 1, 0. And then we can clear out the entire bottom row here by doing R3 and replacing with R3 minus R2. And we get 1, 2, 1, 0, 0 minus 3 minus 1, 0, and 0, 0, 0, 0. All right, so now, of course, we are going to leave these guys alone, and we can let x3 be equal to t. So then that first equation, negative 3x2 minus x3 has to be 0. That gives us minus 3x2 minus t needs to be 0. Minus 3x2 equals t. x2 equals negative 1/3 t. And then here we get x1 plus 2x2 plus x3 needs to be 0. So that gives us x1 minus 2/3 t plus t needs to be 0. That looks like it's going to be 1/3, so x1 needs to be minus 1/3 t. So for lambda equals 0, eigenvectors are of the form. So what do the eigenvectors look like? Well, they look like minus 1/3 t, minus 1/3 t, and t. There we go. So for our first eigenvalue of 0, the eigenvectors are of this form. Notice that there are an infinite collection of eigenvectors, but they are all of this form. In section 7.2, we will define the concept of the eigenspace, because this actually is a vector space, and in this case we would see that the eigenspace, the collection of all the eigenvectors, would be dimension 1 because we had one free parameter here. All right, now we got to go do our other eigenvalues, right? So we had lambda equals 1 and lambda equals 5, so let's go ahead and do those. So we'll need a little bit more room. So let's do for lambda equals 1, we need to solve equation a minus 1 times in v equals 0. So what that means was we're going to subtract 1 off of the diagonal and then augment that. So that means we're going to have 1, 1, 1, 1, 1, 1, 3, 3, 1, augmented with 0, 0, 0. So all I'm doing there is I'm removing my eigenvalue off the diagonal, which is what this 1 times the identity matrix is going to do, and then augmenting it with 0. So it should be pretty easy there. We're going to take R2 and replace it with R2 minus R1, and R3 and replace it with R3 minus 3R1. So we'll get 1, 1, 1, 0, 0, 0, 0, 0, and then 0, 0, negative 2, 0. All right, we should be able to go ahead and back solve. We could go, of course, interchange these guys, but we should be comfortable just using this guy in the middle there. Obviously, we want to avoid parameterizing here and here, so we will instead let x2 be equal to t. Then our first equation, negative 2x3 equals 0, means x3 must be 0. And then the other equation, x1 plus x2 plus x3 needs to be 0. So we would get x1 plus t plus 0 equals 0, and x1 needs to be equal to negative t. So for lambda equals 1, eigenvectors have form. So they would be of the form negative t, t, 0. So in section 7.2, again, we would talk about the eigenspace for lambda equals 1 to have dimension 1, because, again, this had one free parameter for the eigenvectors. All right, we've got to wrap up this with lambda equals 5, which I believe our last eigenvalue. So we'll do lambda equals 5 there. So let's go ahead and do that. One more page here for lambda equals 5. So we need to solve a minus 5 times in times v equals 0. So again, we'll be subtracting 5 off the diagonal and then augmenting with the 0 vector. So that means we'll be getting minus 3, 1, 1, 1 minus 3, 1, and 3, 3 minus 3, augmented with 0, 0, 0. All right, once again, maybe it's easier to pop that guy up top. So we'll interchange R1 and R2 to begin with. So we'll get 1 minus 3, 1, and then 0. And then minus 3, 1, 1, 0. And then 3, 3, minus 3, 0. Now we can use this guy to clear out the stuff below. So R2 will be R2 plus 3R1. And R3 will be R3 minus 3R1. So we'll get 1 minus 3, 1, and then 0. And then 0 looks like negative 8 and 4. Yep, and 0. And then down here we'll get 0 minus 3, so that's going to be 9, 12. And then minus 3 and minus 3, so minus 6. 0. All right. Maybe a little bit hard to see, but actually this guy and this guy are actually scalar multiples of each other. So what we can do is maybe we can start with just a nice 1/4 of R2, just to clear things up a little bit. 1 minus 3, 1, 0, 0, negative 2, 1, 0, 0, 12, negative 6, 0. Then we can do R3 and replace it with R3 plus 6R2 right there. And when we do that, we get 1 minus 3, 1, 0, 0, negative 2, 1, 0, 0, 0, 0, 0. There we go. So now we'll avoid parameterizing these guys here. And then we'll go ahead and we'll let x3 be equal to t. The first equation will be negative 2x2 plus x3 is supposed to be 0. So we'll get negative 2x2 plus t is equal to 0. And looks like x2 should be 1/2 t. Then the other equation, x1 minus 3x2 plus x3 is supposed to be 0. So x1 minus 3/2 t plus t is supposed to be equal to 0. So it looks like x1 is supposed to be 1/2 t. So for lambda equals 5, right, eigenvectors are of form 1/2 t, 1/2 t, and t. There we go. So if for lambda equals 5, we get eigenvectors of this form. So notice that for each separate eigenvalue, the eigenvectors have different forms. So it doesn't really make sense to say the eigenvector of v. It's the eigenvector for corresponding eigenvalue. So these are the eigenvectors for lambda equals 5. These are the eigenvectors for lambda equals 1, and these guys were the eigenvectors for lambda equals 0. So you always want to talk about eigenvectors for the corresponding eigenvalue. All right, so this is our first example of going through and computing eigenvalues and eigenvectors. In our next video, we'll do a couple more examples of just computationally going through, finding eigenvalues and eigenvectors, and seeing some of the different things that can sort of arise. What was sort of unique in this case, and something we'll discuss a lot more as we go forward with this, is that this was a 3x3 matrix, and we had 3 distinct eigenvalues. That is sometimes going to be the case, but sometimes we will see that there might be situations where we have repeated eigenvalues. Remember, we know that the characteristic polynomial is always going to have the same degree as the size of the matrix. So you can never have more eigenvalues than the size. But there are situations that we'll see in the next video where you have less eigenvalues than the size. So you might only have 2 eigenvalues for a 3x3 matrix. And we'll talk about that situation in the next video.